Good evening. Welcome to this edition of the 2018 Heinz-R-Pagels Free Physics Talks here at the Aspen Center for Physics. My name is Josh Freeman, and I'm currently the Vice President for the Aspen Center. I'm based at Fermilab in the University of Chicago, which is also where tonight's speaker is based, Brian Nord. Brian, who will be speaking to you tonight, is a staff scientist at Fermi National Accelerator Laboratory in Batavia, Illinois, and is also a senior scientist in the Kavli Institute for Cosmological Physics at the University of Chicago. Brian got his undergraduate degree at Johns Hopkins University and his PhD in physics at the University of Michigan, and then came to Fermilab as a postdoctoral researcher, working primarily on a new cosmic survey called the Dark Energy Survey, which is where these images were taken. It's a survey being done with a 4-meter telescope down in Chile. While he's been at Fermilab, Brian got quite interested in applications of machine learning and artificial intelligence to questions of the cosmos. And that's going to be, I think, the main focus of what he's going to talk about today, and more broadly about artificial intelligence and machine learning, and where that exciting field of research is heading. I should say, in addition to his work on machine learning and connected to it, Brian has played a number of important roles in the Dark Energy Survey, both as co-coordinator of our strong lensing working group, as well as really spearheading our efforts in education and public outreach, which he's also now extended to his work at the University of Chicago. I should say that I've worked closely with Brian for a number of years. I think I really got to know him a bit better when we were both down in Chile a few years ago observing for the Dark Energy Survey. And Brian was actually my boss while we were down there, telling me what to do, telling me how not to break the telescope and the camera that we were using. And I did listen, yes. So before turning it over to Brian, I just want to mention that this is part of a regular summer series of talks that we host here at the Aspen Center. The next one will be on July 19th by Premi Chandra from Rutgers University, who will talk about the inner universe of quantum materials. I urge you all to come out to that talk as well. Premi and I were actually in kindergarten together, so I've known her even longer. So tonight we're very pleased to have Brian Nord tell us about AI in the sky, intelligent machines in science and society.
Thank you, Josh, for the very kind introduction. How's everyone doing tonight? Are we pre-wine or post-wine? Or mid-wine? Pre, okay. I wish I don't have any in my bottle. I should have done that, though. So Josh is almost right about this picture. Does this sound good? Okay. Josh is almost right about this picture. That is the Gemini South telescope. And on a mountain, I forget in which direction is where our telescope is. And what you're seeing is the Milky Way set during the night and then rise again. And you're looking directly into the Milky Way here. Okay, so we live in the plane of the Milky Way. And I wanted to show you this picture because it reminds us of a thing that we all share. This is our sky together. And as this is our sky all together, this thing that we share, we're also starting to share something else, and that really is our data. We're starting to share our lives with each other through this, through all these ways, these methods, these softwares that put all of our data together and then try to learn about us. And that's part of what I want to talk about tonight. Before I get into that, I want to first also thank the Aspen Center for having me. I really appreciate this opportunity to talk to you. I also want to thank you for being here. And since you're here, and this is a lot of people here, this is your time, This is also your chance to ask questions, so I don't want to just talk and you guys just sit here and be like, oh, I hope I understand this. I'll stop at times and ask if you have any questions, and we'll take breaks. And if we don't get to the end, we don't get to the end. It doesn't matter. This is our time to figure out how this stuff works. And then finally, I also like to acknowledge the Ute people who were the original inhabitants or stewards of this land before colonizers arrived in the late 1800s. I think it's important that, especially, well, always, but especially right now, that it's important to remember what these lands' histories are. So this is the main topic tonight. We're going to talk a lot about AI and artificial intelligence and the buzzwordiness of that. And we're also going to talk about its applications to science and society. And I'd like you to walk away with a sense of how these algorithms actually work. They are black boxy, even to scientists. We consider them, and computer scientists who invented these things, they see them as black boxes. But I want to give you a sense of that they're a little bit more transparent than that, and we can understand a little bit more. I'd like to ask, who here has ever written an AI algorithm? Okay, so we got 3. We got a scientist I know in the back. We have a scientist maybe in the middle that I don't know. Okay. Who here has interacted with an AI algorithm? Okay, everyone who has ever used a phone or a computer or Netflix should be raising their hand. Okay. Okay. I also want to thank the crew, actually. So they helped me figure out how to we figured out together that there was no way to set up the remote for this system, which forced me to learn how to use my phone as a remote for Keynote. So that is possible. Okay. Maybe. It is. Okay. So to give you a sense of how I see myself, and myself in context. So my parents think I'm making the Matrix. Society, I won't say rightly, but not completely incorrectly, thinks that maybe we're creating future machines that could be harmful. My fellow scientists, astrophysicists particular, perhaps, not all of them, but many of them think that I work in a black box. Actually, AI experts think that I'm just a child playing with Legos. And this is what I feel like I'm doing, okay? And I'm not the best programmer, but I'm okay. But the era that we're in with machine learning and computer science is really experimentation. So it feels like we're really just trying to figure out this algorithm, see if we can get it to work on something, and then understand why. And that's sort of comfortable for a physicist in the sense that we grow up with the stories of particle physicists and astrophysicists in the mid-20th century doing stuff on tabletops, just experimenting to see what comes out of it and see what they can learn next. So even though we don't like not understanding what's fundamentally going on inside these algorithms, it's not unfamiliar territory. We have adjustment. Okay. So this is where I want to go tonight. And like I said, we don't have to get to all of this. We can even skip things if people want. But I want to give you a sense of the landscape of how I think AI is everywhere-ish, and that might help you develop your sense of where it could then go. Your imagination could maybe tell you where it's going to go. And then I want to review the history of machine intelligence, another way to say artificial intelligence, a slightly more perhaps accurate way or precise way. And then talk about how machine learning, machine intelligence actually work, and then how it's been applied to astronomy, and then what that implies for society. One thing I learned from getting here to Aspen is that it's even drier than the mountains in Chile where I observe. So. Okay, so robots, intelligent robots, sometimes dancing, are everywhere. And this has led to a kind of crazy amount of hype. Like you see AI in like at least a 10th or 20% of articles that are just coming out. And what often happens with an overhyped technology is that it'll go way up and then it'll hit some peak early on and then drop and then hit some plateau of utility. I don't think that it's, so right, I'm not sure if it's hit the peak yet, I'm not gonna comment on that, but I think there is a danger of it being overhyped, but I think, at least in science, that it's gonna be on this trajectory that is more or less, that has some positive slope to it. I don't think it's gonna go away. I think it's here to stay, both in science and in our lives. So you may have heard of self-driving cars. They can deliver your beer now. Okay. They are translating languages without a dictionary. So I find this actually really fascinating. It used to be that some of these computer programs that would translate from one language to another would go from, say, German to English to Spanish, where English or some other language from a geography, from a place, would be the intermediary language. That's not how it works anymore. The languages, or the algorithms, learn an internal language themselves that then they go from German to the internal language to English, and then to any other. So it's not going from one to the other. It's not going from one language to another anymore. It's going to this internal, algorithmically learned language. Netflix. This is not my cue, by the way. I have much worse taste. If you have leftover things in your cupboard, AI, sort of not the fanciest, but this is one of the overhyped versions of this, might tell you how to turn all your fixins into something you can actually eat. Deep learning, another word for machine learning or AI, can also tell us about, can compete with your general practitioner in identifying some diseases, heart diseases, skin diseases. Artificial intelligence is helping find different molecules, different drugs by mixing together different kinds of molecules and finding what actually can fit together and be physically made. It's finding new kinds of materials. And perhaps more interestingly, it is solving these extremely hard problems, and they're beating humans at it. So chess is almost literally child's play compared to Go when it comes to computing. But I don't think there's been a human that's been able to beat this AlphaGo algorithm from Google's DeepMind. It even does art. Can anyone tell me which one of these is real and which one was made, or sorry, I won't say that. Which one was made by a human and which one was made by an AI?
The right one.
So sorry, I'll ask that in a better way. Which one was made by AI? The one on the right was made by AI. Left. This one. This was made by a computer. Okay, so let me go back. Any questions? Any concerns? Are you worried about the future yet? Okay, so I'd be interested to hear if there are any big examples that I missed at some point. So if you have some in your mind, think about them for later. Yes, ma'am.
Today, Mark Zuckerberg was on Facebook apologizing because his algorithm threw off the Declaration of Independence as being unfriendly or unsuited to his community. Can you tell me how that might have happened?
So the question was, thank you. Yeah. So the question was, some guy by the name of Mark Zuckerberg was saying how some company that he made mischaracterized the Declaration of Independence as unfriendly.
Unfriendly for his community.
Unfriendly for his community. So there's a lot in that, and there's a lot of it that I'm not going to touch. But the technical side of what I will talk about. No, it's an important question. Is that these algorithms are far from perfect. That's why you don't see Aspen taken over by self-driving cars. It's why you don't see us wearing these ear pods that translate to us each other's languages immediately. The algorithms are imperfect and they're biased. They're biased because the way that we develop most of these algorithms is by feeding it lots and lots of data that we have that is typically what we call labeled. And then that labeled data is what the algorithm learns, and then it predicts new things based on that. So another way to say that is good stuff in, good stuff out, garbage in, garbage out. More importantly, I would say, we as humans are still writing these algorithms. We are writing these algorithms. The algorithms are doing the learning, but we're writing them, and we're also selecting the data that goes into them. So our bias, our thoughts and ideas about the world are somehow going to be injected into those algorithms. That's a great question. Thank you. Okay, a little bit of history now. Let's put some of this in context. I don't know what year this was made. I don't know what year this computer was made, but I am remembering from the mid-1980s when I was a kid, we had one of the first portable laptops that was almost as big as the suitcase that I carried here. And it was just this little keyboard that came off the top of it. So that's a little blast from my past. So what is this ecosystem of artificial intelligence? Okay, let's do some jargon here a little bit. And then we're going to throw it away, but I want you to hear what all the buzzwords kind of mean. So AI is this outer scope here. Okay? AI is this idea of algorithms learning from data. And inside that, you have things like you have machine learning. That's a more general term. And AI, I'll go back a second. AI is general in the sense that it's what you imagine from the Terminator movies. It's this thing that we may never have, this generalized intelligence that could like take care of our world for us. That's kind of where this lives in terms of scope. And machine learning is the more practical aspect of that we see used commonly in science and in society. Then representation learning is a more specific thing where you're asking the algorithm to learn the distinct patterns in the data that humans wouldn't be able to see. So it's finding circles, squares, it's finding adjectives, consonants, groups of words. So it's learning the representations that are smaller than the actual data itself, that are condensed in dimension, you could say. And then deep learning is a specific version of that involves neural networks. And typically, if you're talking about self-driving cars and a few other of those applications, it involves things that are based on images. So deep learning today is often thought of with images. But in general, I try to get away from all of that. And I just like to think of these as models, mathematical models that are driven by the data. So I don't have to put in a parameter or a constant like the speed of light or how many, the size of this room or something like that. I don't have to put in a constant to explicitly tell me something about that function. That function, that model, learns all of the pieces of it. Okay? So it's driven by the data. It's not driven by anything that's physically motivated, except the way that I construct the algorithm, you could say. Okay, so historical timeline. AI is not new. This is not the first time that we've explored artificial intelligence. I'm not gonna, it doesn't really necessarily start with Ada Lovelace, but I think I would be remiss if I didn't mention her because she was the first computer programmer. And then, it was 100 years later that we started to get to this point of AI. I'd also be remiss, especially since I'm gonna mention one of the computer scientists who made today's computers possible, that today is Lgbt Stem Day. This is the first annual day of appreciation and acknowledgement of the difficulties that people in the LGBTQ community go through, particularly in STEM, the science, technology, engineering, and math. So a whole bunch of science institutes, the Dark Energy Survey, Fermilab, a bunch of these places said, hey, we're gonna recognize these folks, and they turned their logos into rainbows to remember that a lot of our community is made up of people who are from that background or from that community. So the reason I brought that up partially is because Alan Turing, who brought us in the mid-1940s, comp-sci theory, was a gay man who was persecuted for his beliefs and eventually died, or not for his beliefs, for who he was, and died because of that. So, but he brought us this in the 1930s. He brought us comp-sci theory. Some could argue that he helped end the fight against fascism in the 1940s. He played a pivotal role in early computer science and in bringing us to bringing us into the first age of AI. In 1943, McCulloch and Pitts came up with the idea of the computational neuron for the first time. And then in 1956, there was this conference at Dartmouth College, or is it university, at Dartmouth, where they said, hey, let's get together for 3 months over the summer and figure out this AI thing. They thought that it was going to take a few months and we'll figure out how to make an artificial generalized intelligence that will help us solve all the world's problems. And then in 1973 came the Lighthill report. So this dude named Lighthill said, yeah, y'all promised a whole bunch and you did not deliver, okay? In 1980, Fukushima came up with a modern version of the computational neuron, which he called a neocognitron. Kind of sounds like a transformer. 8 years later, Jan LeCun, who was considered one of the godfathers of modern AI, turned that neocognitron into one of the modern neural networks that we see today. And then in 2012 was a real seminal moment for this current age of AI. And I'll come back to that in a moment. And I already mentioned AlphaGo as kind of where we are as we're in the age where computers are beating humans at these complicated games, and we don't know if we can beat them. So I showed you all these dates. Now let's punctuate this a little bit. Because of the overpromise of the 1950s, we had our first AI winter in the mid-1970s when people were like, no, AI's dead, don't ever do AI again, don't talk about it, it's cold fusion, essentially. So in that case, it was because the architectures weren't as general as they promised. The algorithms couldn't generalize to many different kinds of data. And then in the mid-90s, they had maybe figured out some of these architectures, but the algorithms couldn't be computed. They couldn't be trained fast enough. So that was our second AI winter. And then the new summer, I hope we're still in summer or maybe spring, is when machines got better at classifying images better than humans. So it's not AlphaGo, it's not Go, but it was 5 years ago. But 5 years ago, computers got to be about better than humans at telling differences between giraffes and fire trucks and kids and dogs and things like that. That was the ImageNet challenge. So what made it possible to have this third age of AI, and why are we still in it? Who's heard of NVIDIA? Okay, so they make GPUs, and they used to make them largely for computer games. It turns out GPUs are super efficient at training neural networks. So first, we had Zach Galifianakis, of course, genius, figuring out how these algorithms work. People like him or smarter than him figured out how to optimize these functions efficiently. And then NVIDIA came along and made faster and faster computing, much later than whenever this was made. So those again are called graphical processing units. And then finally, we had big data. So these neural networks could be trained on thousands of pictures of giraffes and cats and fire trucks. And because the neural networks could be trained on these things, they could learn from those images. So we had big data. So thousands of examples per object could teach these algorithms the patterns that they needed to learn. So I'm going to do a little bit of a mathematical digression, which I alluded to a little bit earlier. Oh, yes?
Haven't we always had big data? Is this just the first time we've been able to put it in a package or whatever so that we can work with?
Like, people have always had pictures of stuff, but yeah, people hadn't really collected them into these curated sets of examples and then used them in this context, right? So you could go find on Google a bunch of pictures of a bunch of different cats, but people had not put them into this sample and then run these kinds of algorithms on them. So we've had data for a long time, but the internet coming along made it more accessible to putting all these pieces together. Yeah. So there's been stuff around us, but yeah, so I guess that's a good point. So the stuff around us, there is data flowing all around us, and there's been big data, but now it's curated, now it's used. So another example of this is that medical technology and its use of AI is currently inhibited by the fact that there is not sufficient curation of enough data to be able to train these networks. So people are working in the background now. So Google's doing a bit of this. A few other companies are trying to create these huge databases and collaborations to put together this data to be able to use it. That's a good question. Okay, so I'm going to do something generalized, and then I'm going to give an example. And then this will be a bit of foreshadowing for later. Okay? So when I want to do some math, when I want to think about how to find patterns in data, my neural net over the years has learned about patterns. And so I can see a straight line in this data. And that the data here are the x's. So this is the x coordinate, that's the y coordinate. And then p is some parameter, some physically motivated parameter, some parameter that I see. So in this case, say p is the slope of this data. It's how angled it is from the horizontal. So even if I have this noisy data, I can see a pattern in it. I can say, oh, that looks like a straight line. Then I can write a function that looks like a straight line with some algebra. And I can say if I put in x, then I'm going to get pretty close to what the right y is. So this is, in a sense, you can think about this as a function that has input data and constants with physical motivation. And I'll make that more, I'll make that starker in a moment. With machine learning, it's not all that different. There are key differences, but it's not all that different. I can write another function, that's g. I can use the same input data, and now maybe I haven't drawn the picture here because I want the machine to learn it. Now these are parameters that are not physically motivated. So this is a difference here. I can do a line fit, and I can do a machine learning thing, or I can choose parameters, I can let the machine learn them, the pattern is still there. There's still this slope, there's still this line, okay? So I point this out because this is normal-ish, and this is what we're asking machines to do, but it's still just a function. It's still just a model of the data. It's a more complex model, but it's still a model. Okay, so since we're going to talk about astronomy, just an example of a way to think about this is, if I look at a galaxy, I see how much light there is, and I can maybe find a pattern that tells me how much it weighs. Okay. It's not exactly a spoiler. In about 20 minutes, this will come back, either to haunt us or to help us. So again, you can see there's a constant, there's a slope here that either I could learn or I could write down, the machine can learn, and I can input a luminosity and get out a mass. Okay, before we go to this, any questions about this other stuff? Yeah.
This is a real simple question.
Let's hope.
If I want, to use your example, to have assistance from a machine, a computer, regarding cats, and I want to design an algorithm to help that computer recognize cats, what do I put in the cat algorithm that allows the computer to learn from mass data images?
So the question was, if you want your computer to learn what cute cats look like, what do you have to feed into it for it to learn that? So this brings up an interesting point that I hadn't considered talking about, but you have to tell it what a cat is and what a cat isn't. So you give it pictures of cats and pictures of Brians, okay? Whatever you want it to be. So, but you have to give it something to disagree on or something to say this is not a thing or this is a thing. Yeah. And that's, I mean, and the more different that they are in a space of parameters that I don't know how to write down, and the more different they are in that space, the more likely the algorithm is going to be able to learn that those things are different. So a ball versus what is infinitely different from a ball? I don't know, but the square maybe. But yeah, so things that are different you have to give it. And so the more classes of objects that you give these, the more not the more distinct, but perhaps the more numerous of examples you need to provide of each category of each class. Yeah.
As the computer tries to learn, is the response to it a yes or no or a grayscale?
Very good question. So the question is, as the computer learns, is it binary or is it on a spectrum? Is it yes or no or is it somewhere in between? You can do both. So we can, yeah, I don't know how to say it more succinctly. You can do both. There's a slight change to the network in the computation, but yeah, you can do both. Okay, so let's dig in. What is a neural processor? It is a learning computer, of course. So I gave you this context, all right? So let's dive in and let's think about what deep learning is, and this is a kind of neural net. So I want to talk about two kinds of learning that happen with us and happen in the world. So there's supervised learning, where if someone sleeps enough in class, then they learn to clap immediately when they wake up. Okay? So you're trained for that response over time. Okay? That's supervised learning. That's because you're giving it data. You're telling it what it's supposed to be learning. And there's unsupervised learning. So when you spill milk, maybe that's a way to think about, oh, this thing is broken, and I need to adjust my neural net immediately. I couldn't find a much better example of unsupervised learning, actually. So if anybody has better examples, let me know. So we're going to talk about supervised learning, though, because that's what is most in use in many applications today. So this is a schematic of a neural net. Here are the first sets of neurons, and I'll dig into that in a minute, but I'll say it now, and I'll say it again in a minute. These are just functions, kind of like the ones I showed you earlier, f of x comma w, or g of x comma w. And these functions operate on the images. So they take in a pixel and they do something to it. So they spike it up, they make a pixel go really high. And then each subsequent layer of these pixels does things to the images that are modified coming out of those. So what this in effect does, each layer learns a different specific representation of the image. So when I put in this picture of the Audi, this first layer learns what edges look like. The second layer learns what edges plus a curve look like. And this final layer kind of zooms out and sees the car for what it is completely. Okay. So when you hear learning, we talked about that, these are algorithms that are figuring out what their constant should be. When you hear deep, that just means there are more layers in this neural network. So it's not deep, it's just deep. Okay. So let's do an example. So cats and dogs, there you go. So these look different to me. That's why I chose these. They're both cute, but you know. But if you put these guys into a neural network, this is one that I'll use for a few examples. Again, this is increasing depth with more layers. And these are called hidden layers because this is where the images go in, so you have all the data here. But this is where kind of the magic happens. And unfortunately, some of it still feels like magic. But that's where these parameters in your function are learned. Now, what am I talking about these parameters? Let's get specific about that. So we said there are these, in a model that I could make, a line that I can draw, there are these maybe physically motivated parameters, p, or constants for a function, where x, the data, is the input, and that's a variable because that changes as I feed it different images. So if we look inside, what each of these circles actually is like I said, a mathematical function with a constant for each of these ones has a constant w and a constant b. So it's like a slope and a bias, okay? And this x is the data. And so when data goes through here, this w is modified, or this function acts on these images, and then the images are changed, they look different, and then another set of w's here acts on the images, and then you have an output layer. So they're just these simple functions for each of these neurons, each of them acting mostly independently on these images from layer to layer. So if we put this together, what we're actually doing is we're putting a picture of a cat, a little kitta, we're going into the input layer, and then this hidden layer acts on this cat, makes it look different, and then this next layer acts on the cat, makes it look different, and then you get an output, and this is where your prediction is. This is your yes or no. So if it's yes, then that's feedback to the system. If it's no, that's also feedback. And because what you're asking is, what's the difference between the truth, which you know it's a cat, and what this thing predicted? So this is the truth, and this is the prediction. Okay. So if it says yes, that goes back into, that makes this number very small. If it is a cat, because this is a cat. If it's very different, then this number is very large. And depending on the size of this difference, all of these neurons are then changed. So the w's in that function are modified every time you send an image in, and it learns whether it guessed the right answer or not. So it's really guessing and checking, and that's how it's learning. Okay. So as I see it, the collective power of all these neurons, so if you count this, you can count, there are only 1, 2, 3, 4, there are only 12 neurons here. Right? But most of the algorithms we run have thousands, hundreds of thousands. So these are, the collective power of these computational neurons is that each layer, as an ensemble, identifies distinct features in the images, like lines and circles. And then altogether, the neural networks form a framework for creating these very sort of high-dimensional, complex, and highly generalizable functions that can map this data. So we saw this layer here, so we can count those 4 layers. And then these are some layers that have been, or these are some neural networks that have been used for real tasks over the years. So here's about a dozen layers, and then, actually I can't, we're gonna have to, yeah. So they can get really, really big, okay? And then who knows how big the neural network will be that will make this dude from Star Trek. We'll have to see. Okay, before we get into some astronomy, I guess I have 20 minutes left, is that right? 20? Okay. Any questions about the neural network business specifically? Okay. Oh, it's hot in here. So where does this come in for astronomy? So I thought I'd do is take you on a quick trip of what it actually takes for us to go like find this data that we're looking for. Typically, I'll leave Chicago near Fermilab, and about 22 hours later, I'll end up at the dormitory that I'm going to sleep at night. So I'll go from Chicago down there up to Dallas, and then all the way up to Santiago, and then back down to La Serena. Okay. If people are confused about the map, it's just because I like drawing it a different way. I don't think we need to always have it the other way. I think that gives us a bad perspective, I think. So once I get off the plane, I get into a taxi that I try to speak Spanish, remember from my childhood years, and then I fall asleep inevitably. We go up the mountain, accidentally take a picture of myself. Okay. We see some of the clouds, but eventually, during the night, it's mostly clear. That's why we're up in these mountains. So this right here, this is the dormitory where we sleep and eat. These are a bunch of small telescopes that are run automatically, mostly. You can see them kind of open up during the night. So this is another time lapse. Oh, that was me, I think. Yeah, I was going up the little trail there. Okay. So there's sunset. This is a mining town in the distance. Chile mines a lot of copper. Does anybody know what that is? Moon. That's right. And it was kind of in the middle of the Milky Way, so it really outshines the Milky Way. And then, finally, we get to the mountaintop. So this is the Large Magellanic Cloud and the Small Magellanic Cloud. These are dwarf galaxies that are right on the outskirts of our galaxy. And this is the place where we work, where we have been working for the last 10 years, 12 years. We've just been taking data for about 5. So here's the dome. This little R2-D2 has this dome here. Opens up, the telescope looks out there. This is a human-sized door. Another nice picture that our photographer, Fermilab Ryder Hahn, took. Again, human-sized door. And here's the telescope that we use. This canister, gas canister here, this is a fisheye lens, so it's a bit warped, but this is a human-sized gas canister again. And this whole thing weighs about 1/7 of the space shuttle. That includes this big blue hunk here that helps move it across. And something like a few brachiosauruses, if you like to count in dinosaurs. So light comes from up there, comes down to this mirror, and goes into the camera where there's a CCD that's just a few $1 million times better than my phone. And then over the course of the night, so there's nobody inside that dome at the top that's looking at stuff, because any human in there would mess up what the images are being taken. So the telescope works semi-automatically. We give it a few instructions, and then it goes throughout the night as much as it can. So you can see it kind of tracking the sky as the dome moves. And this is one of the pictures that we took. This is one of the earlier pictures. So this beautiful big blue galaxy here is amazing, but it is also annoying. Okay, it looks great, but what I actually want to measure are the hundreds and thousands of galaxies that are behind it. Because that statistical data, that big astronomical data, or beg your pardon, that astronomically big data, is how we measure things about the universe. We need more and more galaxies. We can't just do a few here and there. So this is a bit better of a field for us to look at. And then from the Sloan Digital Sky Survey, when you put all that data together, you can start to see patterns in it. So in each of these pixels are many, 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 many galaxies. This is actually a very large swath of the universe that Sloan Digital Sky Survey took over about a decade. So where does that leave us? So I just wanted to give you a sense of, this is one way that we represent the data. And from this, we've learned about dark matter and dark energy existing. We've learned that we, as things that interact with light, make up only about 5% of the universe, dark matter and dark energy making up all the rest of it. And what does that mean for our future? So a colleague of mine, grad student, University of Michigan, back in the day, he made a simulation of the universe. Often we make these simulations that go from the past to the present, and this one is going from the present to the future. So it's asking what happens. So Michael Busha asked, what happens in 50 billion years? What I want you to do is, I want you to pick a particle on this screen, and I want you to watch it, okay? And what you're gonna see, it's gonna look like you're zooming in, but it's actually the space-time expanding. All right? So pick a particle and watch it and see where it goes. And if it goes off the screen, will it come back? So spoiler alert, a lot of them don't come back. Okay? So what is going to happen in about 50 billion years is that gravity will win on smaller scales and take individual galaxies and whomp them into these large megagalaxies or clusters. But while that's happening, space-time expansion will push these megagalaxies away from each other. And they'll eventually be pushed away so far and so fast that they'll be moving so quickly that light will not be able to get from one to the other. So if we did astronomy in 50 billion years, it's questionable whether we'd be able to learn about these phenomena through the means that we do today. That's one way that this universe that we're in could end up. So I wanted to present this to you so you have just a sense of why we're trying to do these things and a little bit of why we might need machine learning. So I'll get to that in a second. So this is another way to look at the universe. This is a summary of what we know. We know it was really, really small at some point. It went, oh, and it got big really quickly, and then it grew slowly, and now it's growing faster and faster. And this accelerated growth is what's leading us to having these island universes eventually. Okay. All right, before I go on, any questions about the astronomy? There's a little bit more astronomy to come, but this is general stuff. Yeah.
Still controversial. I mean, there are people who say that it doesn't exist and people who say that it does. I see papers arguing both sides.
So I'll say my opinion is that it's similar to climate change in that most people believe that it exists, but there are a few people who are still trying to find models where it won't. And I'll also say that I'm not enough of an expert to say that those models are exactly incorrect, but I don't trust them. I trust the evidence that I've seen from dark matter much more. There is a question about what dark matter is. So we're pretty sure that it exists astrophysically, but as a particle, we'd like to be able to make it or know exactly what that particle is, and that is still a matter of intense debate. Scientists are probably making bets right now. You know, these $1 bets that Stephen Hawking used to make about when it will be discovered. I'm not going to make that bet. Okay. So let's dive in a little bit into one of the things that I really care about, which is strong gravitational lensing. And I really like strong gravitational lensing because it exquisitely embodies John Wheeler's description of general relativity. So if you remember this, John Wheeler said to describe general relativity, he said that matter tells space how to curve, and then space tells matter how to move. And that's exactly what's happening in a strong gravitational lensing system. So you've got us here looking out a few billion years away. You've got a galaxy that's nearby us, and you've got a galaxy that's further away. Now, light wants to travel on a straight line. It has to travel on a straight line. But what is a straight line in curved space? So when space is curved by this mass, the light is told to move in that direction. And because light appears to come in a straight line, it looks like it's coming from there. So a strong gravitational lens is this thing looking like this thing. And if you put those pieces together, you see a galaxy in the middle here that is not warped, but it's causing the warping of space-time. And then you see the galaxy behind it that is warped. So I wrote there's a paradigm shift because, well, I'll get to that in a second. I want to give more example, actually. So I didn't get to go here while I was here, but next time, I promise. If you have my friend Eli Reichoff's GravLens app, I think it's on iPhone, you can gravitational lens any image you want. So that means you can put a foreground galaxy in any picture. And you can see the real physics. This is the correct physics of what that galaxy of that size will do to that background image. So if you're standing over here, there's maroon bells, and you said and put a galaxy there, this is what it would look like. Okay. Eli also shows this off by warping his kids' pictures. That's his way. Okay, so why are we in a paradigm shift? It took us about 40 years to find each sort of major species of strong gravitational lens. And I say species because they're hard to classify, but I would say this way I'm defining species is what is being lensed or what is doing the lensing. So in this case, you have a background stellar-like object that is being turned into two stellar-like images. You have a galaxy in the middle there, so it's making it look like there are two things. Then you have a large galaxy cluster that's giving you the first arc that we ever saw. And then you have this really special case where there's a galaxy here, and then there's this galaxy right behind it. And that creates a perfect circle for that set of arcs. And then most recently, the first ever lensed supernovae, or multiply image supernovae, was discovered in 2014. So, and each of these has a different way for us to learn about those things I was showing you earlier about dark matter and dark energy. So it took us 40 years to find 1,000 lenses, but still in these only these 4 different categories. It took us 40 years to do that. But now with dark energy survey, we might just double that number in 5 years of observation. And the survey that's going to start in about a year, 2 years, will find 2 orders of magnitude of these objects more than that. So that's the paradigm shift. We're going to find so many of these objects that this is going to be a new way to actually probe the universe. So what did we do in DES? So we didn't have fancy algorithms when DES started. We didn't know how to use them. So what would we do? We cut up these images, these tens of thousands of images, and we looked at them by eye. And I don't think any grad student should ever be subjected to this again. And we looked by eye and we ranked them. Like groups of 15 said, I think this is one, and then we averaged our rankings, and that's how we decided to go try to confirm that these things are lenses. That took a long time. So here are the numbers that I gave you before. There are about 1,000 today. DES is going to find twice that many, 120,000 from the LSST telescope on the ground. And this Euclid and WFIRST are these new telescopes that will find hundreds of thousands more. So citizen scientists can help with this. I mean, I'm a citizen scientist. I just happen to get paid for it. But they have helped in different ways to classify galaxies, to classify strong lenses, and it's going to be a great benefit because machine learning won't be able to find all of these, but there aren't enough citizen scientists to do all of this work alone. So these are actually examples of lenses that have been found by a graduate student, Colin Jacobs. He works in Australia. So he ran a machine learning algorithm, one of these deep learning algorithms, and he found these lenses which really look like lenses. We have to go confirm that, but these are all high probability lenses. There's a really nice one. It's rare to have one that has a red arc instead of a blue arc. So there's a red arc, there's that lens in the middle that's in the foreground, and then there's that little bit of a counter image on the other side. And then work from people at Stanford and SLAC did a thing that was pretty incredible. So not only do you have to find these things, you have to classify the dogs versus the cats and say lens or no lens, but in order to do science, you have to measure a number, this gray area. You have to measure a mass of the object. And I've been working with a grad student at U Chicago who's trying to model I won't say by hand, model with a physically motivated model. He's trying to do that, doing a computation. And it can take a day, easily take a day to make a model, a simple one, of one of these images. So what the Stanford group is, they applied deep learning, and they were able to speed that up by 10 million times. So there's still work to do. So the part of that black box is that it's hard to measure how uncertain we are about some of these things. But the Stanford group also took strides in that. So we're making progress and be able to use these things to actually accelerate science. Any questions about the lensing? No, we're making good time here, okay. It is hot in here, I understand. Okay, so I want to turn to, well, the question is, are we going to replace that grad student? Right? There are much more complicated gravitational lenses. So I have a friend named Karen Sharon in University of Michigan, and she loves modeling gravitational lenses, but the bigger ones, the galaxy cluster ones, and these have lots and lots of arcs, much more complicated than this. And we talk about it, and she's not super thrilled that AI might be able to do what she can do. But I'm not sure that it's going to go that way. And if you've been listening to the hype, I'm not going to put I'm not gonna plant my flag in a place that says that machines are gonna replace humans for all these activities. I think it's more likely that it's gonna disrupt our workforce, including science, but we're gonna end up working with machines in a different way, just like we ended up working with computers. It's potentially more disruptive than the previous technological revolution, but it's not going to replace Karen. Okay? But it is something that we got to talk about, because our society, most of our societies, don't update people's resumes. They don't update our skill sets fast enough to equip them in a way to work with these new technologies. It can, but we don't do that. So what's going to happen to the entire infrastructure of self-driving cars and self-driving automobiles? What's going to happen to truckers? What's going to happen to the dispatchers? Like those are industries that have that's an industry in America that has 5 to 10 million people, depending on how you count it. Okay. Retail, you already see, you walk through grocery stores and you maybe never have to talk to a human. That's not AI necessarily, but it's automation. Factory is a combination of automation and AI. Andrew Ng, he's one of the other maybe godsons or godfathers of the current AI revolution. And he said for a while that a radiology degree is not the best thing to think about right now, because maybe images can figure out what's going on, or AI can figure out what's going on inside you via images better. And he's been, I wouldn't say taken to task, but he's been pushed back on that. And I think rightly so. I don't think that all general practitioners are going to be replaced. They're just going to learn to work with this technology as we have other technologies. So, but it is important to think about how our society is going to change, especially in the workforce. Additionally, as someone alluded to a little bit earlier, it's not just that data about us is used, it's sort of all-encompassing now. We are the data. People are making money off us. They made a lot of money off me the last couple of days, Twitter did, okay? But we are the data. And when we are the data, people can use us then to maybe train these algorithms and then spit something back out that is inaccurate or imprecise or chosen poorly. Humans are still designing these algorithms that are manipulating or learning our data. So anybody notice, this is related to the last slide, of course, anybody notice something common about this set of pictures? What did I hear? Head and shoulders. Mostly men. Forward facing. What did I hear in the back? Mostly white. Ah, yes. Okay. So they're mostly white. So there are standard data sets in machine learning that people use to compare their algorithms. Okay. One of them is called the MNIST data set. This is a set of handwritten signatures. And people try to test their algorithms to make them faster and say, oh, I did much better on the MNIST data set. There's another one that is about poses, because people are trying to understand like what human shapes look like. And another one, of course, you also want to train your algorithms on a common data set. If you're going to be doing a common data set with people in it, if you're going to be using any of this technology at the airport for criminal justice, you're going to be making these algorithms, and you're going to want to have a common data set to compare these algorithms against. Turns out this common data set called label faces in the wild is biased to have more white people. So it will have no idea what to do with me. For better or for worse? I don't know. In most cases, for worse. So ProPublica did a piece last year where they showed that there are machine learning algorithms that are not public, the code is not exposed to the public, that are used to directly inform sentencing requirements to judges. So judges can look at the output of these sentences. It can't just be the algorithm decides, but the judge is allowed to use that as sentencing. And it is demonstrably, the algorithm that was used in particular, you can go look at this article, this algorithm that was not vetted by anybody except the company and whoever helped it get into the justice system, made it look like he was the criminal, or made it look like he was going to go back to jail or be the criminal, whereas it was him. So it is a measured fact that machine learning algorithms in the criminal justice system are biased against people of color. And it's not just going to be people of color, right? If humans are making these algorithms and humans are in power in these companies, they can make it biased or allow it to be biased against anybody. Thankfully, there are large groups of people who are working on this from a technological standpoint. I'm not going to get into the political standpoint, but these different groups are trying to understand technologically, algorithmically, how to eliminate bias from these algorithms. Something that, in a way, affects more of us, or all of us at the same time, in a more obvious way, perhaps, is that our government is, and probably many governments, are wanting to use AI when it comes to military technology. The Pentagon asked Google to help consult with their neural net algorithms, try to help them figure out how to use them better with drone technology. I was really grateful to hear that a lot of Google employees, I think 8 or 10 of them quit, and a bunch of them protested publicly and said, we don't want you to do this. I think where we are is a really interesting time. And it's a precarious time in terms of this technology. The different countries that have access to building up this technology through their industries, through their corporations, us, Russia, China, many others, they're furiously working to perfect it. So I don't think it is anathema. I don't think that it is at all beyond the pale to say that this is a race to develop this technology between nation states. And that's something that we all should care about, I think. This is an important moment in history. So these are I want to make a few comments after this, but these are mostly my final thoughts in that I think that AI has been so transformative because it really bridges between different technologies or different spaces of our existence and thinking. This was 6 years ago. Google wrote an algorithm that could write a sentence to describe this image. So they were writing algorithms that could capture an image for you. That's mixing images and text. And then mix images and text and voice, right? Has anyone heard of deep fakes? Okay, so we got 2. So go look this up as soon as you can get home. Look up deep fakes and Obama. So what you can do right now, so if you had a little bit of savvy, if you've run some Python, you can download code from the web, and you can train a neural network to then be able to generate a new video of someone saying something they have never said before. So if you think about fake news now, okay? So deep fakes? Fake. Yeah, fake, sorry, yes. So yeah, Obama and deep fake is one of the best examples I've seen. Yeah. So I think 2 things then about sort of responsibility. One is that, as a scientist, I'm developing these algorithms to make them better for science. But anybody, the government, anyone else, once I put it up for public, could use it for anything they want. So it's my responsibility to be involved in the ethical discussion of how these algorithms are going to be used. That's my responsibility. And I think as citizens, it's all of our responsibility to understand this technology, understand where it exists, understand where it's being used, whether for us or on our behalves in some way. One way I think that science has been able to accelerate its success with deep learning is because a lot of cases physicists want to be the expert in the room, or we want to figure everything out from scratch. But we work faster when we work with experts and acknowledge that someone on the other side of the table is bringing their expertise and we're bringing ours. So I think that's been a real key to how we've had such success so far. And this is how our research group at University of Chicago works. So we want to learn how deep learning works, but we want to figure out stuff a little bit faster. So we team up with deep learning experts, for example, to do these tasks so that we're not trying to reinvent the wheel at every moment. And I think the bigger picture statement of that is, I think that there's an untapped communication technology. So we're doing this fancy stuff with AI and algorithms, but I think we still have a lot to learn about how to talk to each other and about how to work together with these hard problems. So I'll leave you with that. Thank you.
That was great.
Yeah, thank you.
More questions?
Yeah.
generally believed that we're not too far from quantum computers working with qubits instead of bits. And so assuming that quantum computers come to be, will there be new algorithms for AI based on those advances, or is it just a matter of they'll be bigger and, of course, enormously bigger than what we now have, and we use the same algorithm?
Thank you for that question. I didn't have time to talk about it, so this is perfect. So Google has something like a 500 qubit computer now, I think. And it's not really enough to do serious computations that are just taking the same problem, being able to demonstrate, oh, we can do it now and we couldn't do it before in polynomial time on a regular computer. But machine learning is one of the best applications for quantum computing, because quantum computing can potentially optimize the algorithms much faster, and that's one of the bottlenecks being able to do this. So yes and yes and yes. Quantum computing is going to be great. Hopefully it's not like cold fusion. I don't think it will be. I think it's going to be a real thing, and I don't know how soon. I'm not going to make that bet either, but it's happening quickly. Yeah. Yes?
I've got the opposite question on that. How will AI inform quantum computing? Because according to the quantum computer guys, they're not getting too far with this.
Oh, I've been pretty impressed with their progress, going from like tens of qubits to hundreds in a few years. But I get your point. I mean, that's only a difference of that's times 10 qubits, right? I actually don't know. I don't think we're there yet where AI can say this is what the chip structure should be. I think we're not there yet. And I haven't seen any papers on that. Is anyone else who thinks about this stuff seen AI telling us how to make a quantum computer? No? Okay. Maybe that's for the best right now? Yeah.
How much time you spend in your PhD program on ethics?
Personally or professionally? We don't, in academia, we are not well trained. We have, there's mandated training, either by NSF or DOE, so we go to these few-hour courses, but there's not a lot of official training that we receive, or many of us have time to endeavor to find, to really understand, to think about the ethics. I mean, we were able to take courses, so maybe some of us choose to take a course, but say ethics in the academic environment, that's actually one of the bigger problems that we're facing, and we are not, for generations, we have not been trained well to handle it. Thank you for that. Yeah. I will say though, I guess, I'll just, that there is a bit of a groundswell, more than a bit. There's a groundswell right now. People who are very passionate about changing this. A lot of the people that are here at the Aspen Center actually think about this question hard. Now we think hard about it, and we're learning. But I think we're making progress. I won't say that we haven't gone through a curve to say that, oh, this is we're on the track to making everything better. But we're working hard to make things better.
Yeah, I'm here as a musician with the music festival, just interested because it's so far from my field. And do you have any thoughts on how you could see this further in the arts to help music, whether from performance or education perspectives? What kinds of technology would I be able to suggest, for us to look into, those of us who don't have any experience with this, or arts in general, maybe?
So how would AI inform the creation of music, for example? Or
Yes. Yeah.
so there are algorithms that are generating music. There are algorithms that are generating trailers for movies that are passable as something that maybe David Lynch made. So people are making these complex algorithms to make music. That's an interesting question about what the hybrid would be, though, between maybe the musician and the algorithm. Yeah, I don't know. I probably will have that ready for the next time I talk about this, though. Thank you. Okay. Okay. All right. Looks like people are hot. Let's get out of here. Thank you very much.